Hi, scholarship students. So welcome to, I think we're up to lesson 3. I can't really remember, so we'll call it lesson 3. We're going to do our last session on straightforward types of cells, I guess you could say, or just general redox questions. And after this, we'll move on to redox titrations. So this was a homework question that I set. You guys can read the question. It's pretty much talking about electrolysis, and the solution is sodium iodide. Okay, so it says here, commonly the strongest oxidant in the solution reacts and the strongest reductant reacts. Now, we know this doesn't actually always happen because we've seen many examples before where water actually has the lowest reduction potential, but chloride gets oxidized instead. So I kind of always stick to the rule that when we're doing electrolytic, anions will always go to the anode. So anions will go towards the anode, except for nitrate and sulfate. Those are our two exceptions. The reason why is because nitrate and sulfate are in their maximum oxidation states, and so they can't get oxidized. So that's just something to note. So let's look at this example. We've got sodium iodide. So if we're sticking to that rule, okay, then what we want is we want to see between, well, where's the anion? So the anion is I minus, and it's going to go to the anode. Now, in this example here, they've actually been very clever with what they've chosen, because iodide and water, so those are your two options of the species that could get oxidized. You'll see water's actually got a higher reduction potential anyway. So it works really well here because the species with the lowest reduction potential is actually getting oxidized. So that works really well out of the two that are available, because we don't have H2 and we don't have sodium metal. So iodide's going to go to the anode and get oxidized to I2. And the next part is what's going to get reduced, sodium or water. Okay, so this is the reaction for water getting reduced, and here's the sodium getting reduced. We know that the species with the highest reduction potential will always get reduced, and in this case here, that's water. Okay, it's much higher than Na+. So water is going to get reduced and produce hydrogen gas, and iodide's going to get oxidized and produce iodine. Hopefully that makes sense. Okay, so, oh God, trying to get the page to change. There we go. Okay, so there's the answer. And it produces a negative cell potential, and that's because the species that is actually the highest, the strongest reductant is not available and therefore can't get oxidized, and the strongest oxidant is not available and therefore cannot get reduced. Hopefully that makes sense. Okay, here's the next part of the question. I love disproportionation reactions, and we've done a few of them now. So just to recap, a disproportionation reaction is when the same species gets oxidized and reduced. And so it's saying here, identify the species from the standard electrode potentials given below that are most likely to do this in basic conditions. Justify your answer and write balanced equations. So justifying your answer would be to calculate a cell potential and prove that it is positive. And you must do all of your balancing in basic conditions. So you just need to go through and basically pair up what you can. So it has to be the same species getting oxidized and reduced. So if we look here, because it has to be the same species, we can't start with this ever because there's nothing for it to go to. So we can start with this, and it can get oxidized to this, and it can get reduced to this. Okay, and then we can do a second one where we start with this, and it can get reduced to this, oxidized to this, or it can get reduced to this. And then the third one is using I2. So you can only, where I2 can get oxidized to this or reduced to this. So you've got 3 pairings that you have to do, because remember, you've got to start with the same species. So I'm going to go through and show you them already done just to speed this up. Okay, so here I've just done that little chart, the Latimer diagram, where you can see what can go to what. So I don't know why, for some bizarre reason, I've chosen to start with this species in the middle. It makes no logical reason. You could answer this in any way you wanted to. So these equations have to be fully balanced, and remember, they have to be in basic conditions. So I've already done that here. Okay, so I've got my basic equation. Okay, And you'll notice that I haven't actually at this point cancelled out my H plus and OH minus here, so just bear that in mind, these parts here. So you balance in normal acidic conditions, and then however many H plus ions you've got, you add the same number of hydroxide ions to each side. So that reaction there is reduction because electrons are being gained. Hopefully you don't need me to go through that. You know that if it's getting reduced, that's forming that. So I'll quickly do it just in case. So you've got IO minus forming I2, so we have to put a 2 here to balance out the I's. We've then got to add 2 waters to balance out the O's, so I do that. In doing that, we've got to add 4 H pluses to the other side, and now we need to balance the charge. So you've got 2 minus and 4 H plus and nothing on the right-hand side, so you had to add 2 electrons. The final step of this task is to add the same number of H pluses to each side that you had add OH minuses, the same number as you have H pluses. So because you had 4 H pluses, you have to add 4 OH minus to each side, and then this H plus, these H pluses and OH minuses add to make 4 waters. And so if you've got 4 waters on the left hand side and 2 waters on the right hand side, these get cancelled out. Okay. So that's the reduction half equation. So now we need to do the oxidation half equation. Now the oxidation half equation is going to be when you start with IO minus and you form IO3. Okay, so we're going to do that now, IO3 minus. So the iodine's already balanced, except this time you've got 1 oxygen versus 3. So we need to balance that by adding 2 waters to the left-hand side. Okay. We now need to add the same number or balance the hydrogens by adding H plus. And now we need to balance the charge. So on the left-hand side, you just ignore the OH minuses yet because they're not technically there yet. I haven't used that as a balancing tool yet. You got 1 minus on this side. And then on this side, you have got 1 minus and then 4 pluses. So you need them to be the same. So we have to add 4 electrons. So I add my 4 electrons. The final step for balancing in basic conditions is to add the same number of OH minuses as there are H pluses to each side. So I add 4 and 4, and we know that these will add to make 2 waters, and you've got 2 waters here. So that's going to cancel just like up here. That'll be 2H2O, and that'll be 2H2O. Excuse me. And then you can add everything together, okay, in your 2 reactions, and you should get this overall equation hopefully, and then we can do reduction minus oxidation using the cell potentials from the previous slide, and you'll see that this is a positive 0.31 volts, and because it's positive, this reaction is spontaneous and IO will disproportionate, which is quite cool. So I'm not going to go through all of them in that much detail because we'll be here all day. So here's the second one you could have done. This is I2 getting reduced and oxidized. So there are the 2 half equations. Here's the full equation. And if you do reduction minus oxidation, you get a positive value. So again, this is spontaneous. So I2 will disproportionate in basic conditions. Pretty cool. And the last one here is iodate, which is IO3 minus getting oxidized and reduced. And here's the full equation. Please note that to get full marks in this section of your exam, you have to do the full balanced equation, or else they don't give you full marks. And you'll see that this one produces a negative voltage, and because it's negative, it's not spontaneous and it won't disproportionate. And that's how we answer that question. Any questions, let me know. Okay, here's the next question. So 2013 question. It says, in electrolysis reactions, blah, blah, blah. You guys can read this. It says the strongest oxidant will react at one and the strongest reductant will work at the other one. So this one's interesting because unlike the other one, it says commonly it will, but this one it says the strongest oxidant will react at one electrode and the strongest reductant will react at one electrode. And so this one's also interesting because instead of just having one solution in your electrolyte, they've given you 2. So they've said nickel sulfate and cadmium chloride. So you've got to be quite careful with language here. And because they've said instead of sometimes it can be, they've put the strongest reductant will react and the strongest oxidant. Okay, so what we're going to do now on it said that both electrodes are platinum, which is an inert one, sweet as. And they've even been nice and said the anode is nickel and the cathode is platinum. Okay, so what we're going to do now is we're going to go and have a look at these cell potentials that were provided in the question, and work out what we think is going to happen. So here are the reduction potentials, okay? So you've got cadmium, nickel, you had sulfate, which is here. I think we had chloride. I'll just have to go back and actually read. I should have put that all on one side. That's annoying. So we've got nickel sulfate and cadmium chloride. Nickel sulfate and cadmium chloride. So we've got nickel sulfate and cadmium chloride. Okay, so here are all of our species. Okay, so we've always got to work out, will water get reduced, or will the cations get reduced? And so we're trying to determine which one out of these three at the top are going to get reduced, okay? Because they're the only three that we've actually got in our solution. So the one that's got the highest reduction potential is in fact the nickel, okay? So nickel will get reduced because this number is the highest. So nickel's going to get reduced. So now we've got to see what's going to get oxidized. Okay, so what's going to get oxidized is the species with the lowest reduction potential. And in this case here, so when we're talking here, we've got water, chloride, and sulfate. It's never going to be sulfate, okay? And it's in this example, it's going to be water that's got the lowest reduction potential. Okay, and therefore water in this example is going to get oxidized. This is an interesting one because often we do questions like this, and even though chloride has got often chloride has got the higher reduction potential, but it actually still gets oxidized. So this was a bit of a question where there was a bit of hum and ha in the exam about this, and I do speculate, I don't know, but I speculate that they would have given kids who did chloride here the correct answer, because often chloride does, and it's actually not always to do with the cell potentials, it's to do with concentration and other things. So just bear that in mind, but I'm pretty sure with this question from memory, it was water. So here's me going through. We've already said that nickel because it had the highest reduction potential, and yeah, there we go. And water's getting oxidized, and there's your full equation. Okay, we can do the cell potential and you get the negative 1.48 volts. So a bit of advice I would say when you're doing these scholarship questions is just go with what the question says. Okay, if it says it has to be the strongest, then do the strongest, and it's just the same stuff. I kind of feel questions like this are really not that much harder than what you could have I could have given you in your internal. Okay, and so then you just make a sentence that it's negative and therefore not spontaneous, so therefore needs a power supply. Okay, and then I think the last part of the question was what would happen if nickel was being used in place of a platinum electrode. So if we used nickel instead, nickel would still get reduced because it has the highest reduction potential. But the problem now is that there'd be 4 different oxidation equations. So instead of just those options, nickel, the metal, could also get oxidized. So you'd have to look at the reduction potentials. And actually when you do, nickel is a stronger reductant, and so is more likely to get oxidized than any of the other species, which means nickel would both get reduced and oxidized. And this is an example, if you've managed to correctly identify it, is the same as electroplating. So this is an example of electroplating. And the cell potential would be 0 because it's the same reaction. Okay, yeah, cool. Hopefully that makes sense. Okay, I'm actually going to pause here because we're at 14 minutes, but I'll do a part B now. See you soon.